62, the two laws of circuitation did not start into full activity all at once. On the contrary, although they express the fundamental electromagnetic principles concerned in the most concise and clear manner, it was comparatively late in the history of electromagnetism that they became clearly recognized and explicitly formularized. We have not here, however, to do the work of the electrical todhunter, but only to notice a few points of interest. The first law had its first beginnings in the discovery of Oersted that the electric conflict acted in a revolving manner, and in the almost simultaneous remarkable investigations of Ampere. It did not, however, receive the above-used form of expression. In fact, in the long series of investigations in electrodynamics to which Oersted's discovery and the work of Ampere, Henry, and Faraday gave rise, it was customary to consider an element of a conduction current as generating a certain field of magnetic force. Natural as this course may have seemed, it was an unfortunate one, for it left the question of the closure of the current open. And it is quite easy to see now that this alone constituted a great hindrance to progress. But so far as closed currents are concerned in a medium of uniform inductivity, this way of regarding the relation between current and magnetic force gives equivalent results to those obtained from the first law of circuitation in the limited form suitable to the circumstances. Stated, if C is the density of conduction current at any place, the corresponding field of magnetic force is given by H equals vector product C R1 over 4 pi R squared. At distance R from the current element C, if R1 be a unit vector along R from the element to the point where H is reckoned. The intensity of H thus follows the law of the inverse square of the distance along any radius vector proceeding from the current element. But, in passing from one radius vector to another, we have to consider its inclination to the axis of the current by means of the factor sine theta, where theta is the angle between R and the axis involved in the vector product. Also, H is perpendicular to the plane containing R and the axis of the current element, or the lines of H are circles about this axis. But from the Maxwellian point of view, this field of H is that corresponding to a certain circuital distribution of electric current, of which the current element mentioned is only a part. This complete current being related to the current element in the same way as the induction of an elementary magnet is to the intensity of magnetization of the latter. Calling the complete system of electric current a rational current element, it may be easily seen that in a circuital distribution of rational current elements, the external portion of the current disappears by mutual cancelling, and there is left only the circuital current made up of the elements in the older sense. We may therefore employ the Formula 1 to calculate without ambiguity the magnetic force of any circuital distribution of current. This applies not merely to conduction current, which was all that the older electricians reckoned, but to electric current in the wider sense introduced by Maxwell. But the result will not be the real magnetic force unless the distribution of inductivity is uniform. When mu varies, we may regard the magnetic force of the current thus obtained as an impressed magnetic force, and then calculate what induction it sets up in the field of varying inductivity. This may be regarded as an independent problem. In passing, we may remark that we can mount from magnetic current to electric force by a formula precisely similar to one, but subject to similar reservations. The cardinal feature of Maxwell's system. Advice to anti-Maxwellians. 63. But this method of mounting from current to magnetic force, or equivalent methods employing potentials, is quite unsuitable to the treatment of electromagnetic waves, and is then usually of a quite unpractical nature. Besides that, the function electric current is then often a quite subsidiary and unimportant quantity. It is the two fluxes, induction and displacement, or equivalently the two forces to correspond, that are important and significant. And if we wish to know the electric current, which may be quite a useless piece of information, we may derive it readily from the magnetic force by differentiation. The simplicity of the process being in striking contrast to that of the integrations by which we may mount from current to magnetic force. To exemplify, consider the illustrations of plane and spherical electromagnetic waves of the simplest type given in 53 to 61, and observe that whilst the results are rationally and simply describable in terms of the fluxes or forces, yet to describe in terms of electric current and derive the rest from it would introduce such complications and obscurities as would tend to anything but intelligibility. Now, Maxwell made the first law of circuitation, not however in its complete form, practically the definition of electric current. This involves very important and far-reaching consequences. That it makes the electric current always circuital at once does away with a host of indeterminate and highly speculative problems relating to supposititious unclosed currents. It also necessitates the existence of electric current in perfect nonconductors or insulators. This has always been a stumbling block to practitioners who think themselves practical. But Maxwell's innovation was really the most practical improvement in electrical theory conceivable. The electric current in a nonconductor was the very thing wanted to coordinate electrostatics and electrokinetics and consistently harmonize the equations of electromagnetism. It is the cardinal feature of Maxwell's system, and, when properly followed up, makes the insulating medium the true medium in the transmission of disturbances and explains a multitude of phenomena that are inconceivable in any other theory, unless it be one of the same type. But let the theoretical recommendations, apart from modern experiments, which can only be appreciated after a pretty close study of theory, Maxwellian and otherwise, stand aside, and only let the tree be judged by its fruit. Is it not singular that there should be found people, the authors of works on electricity, who are so intensely prejudiced against the Maxwellian view, which it would be quite natural not to appreciate from the theoretical standpoint, as to be apparently quite unable to recognize that the fruit has any good flavor or savor, but think it no better than dead sea fruit? The subject is quite sufficiently difficult to render understandable popularly, without the unnecessary obstruction evidenced by a carping and unreceptive spirit. The labors of many may be required before a satisfactory elementary presentation of the theory can be given. So much the more need, therefore, is there for the popular writer to recognize the profound significance of the remarkable experimental work of late years, a significance he appears to have so sadly missed. When that is done, then will be the time for an understanding of Maxwell's views. Let him have patience, and believe that it is not all speculative metaphysics, because it is not to his present taste. Never mind the ether disturbances playing pranks with the planets. They can take care of themselves. Changes in the form of the first circuital law. 64. 2 or 3 changes I have made in Maxwell's form of the first circuital law. One is of a formal character, the introduction of the H term to express the intrinsic force of magnetization. This somewhat simplifies the mathematics and places the essential relations more clearly before the eye. Connected with this is a different reckoning of the energy of an intrinsic magnet, in order to get consistent results. The second change, which is not merely one of a formal character, but is an extension of an obligatory character, is the introduction of the H term to represent the motional magnetic force. In general problems relating to electromagnetic waves, it is equally important with emotional electric force. The third change is the introduction, first done, I think, by Professor Fitzgerald, of the term to explicitly represent the convection current or electrification in motion as a part of the true current. Although Maxwell did not himself explicitly represent this, which was a remarkable oversight, he was strongly insistent upon the circuital nature of electric current, and would doubtless have seen the oversight the moment it was suggested to him. Now there are spots on the sun, and I see no good reason why the many faults in Maxwell's treatise should be ignored. It is most objectionable to stereotype the work of a great man, apparently merely because it was so great in advance, and because of the great respect thereby induced. The remark applies generally to the science of quaternions, for instance, which, if I understand rightly, Professor Tate would preserve in the form given to it by Hamilton. In application to Maxwell's theory, I am sure that it is in a measure to the recognition of the faults in his treatise that a clearer view of the theory in its broader sense is due. Introduction of the second circuital law. 65. The second circuital law, like the first, had an experimental origin, of course, and like the first was long in approximating to its present form, much longer, in fact, though in a different manner. The experimental foundation was Faraday's recognition that the voltage induced in a conducting circuit was conditioned by the variation of the number of Iines of force through it. But, rather remarkably, mathematicians did not put this straight into symbols for an elementary circuit, but went to work in a more roundabout way, and expressed it through the medium of an integration extended along a concrete circuit, or else of an equation of electromotive force containing a function called the vector potential of the current, and another potential, the electrostatic, working together not altogether in the most harmoniously intelligible manner, in plain English, muddling one another. It is, I believe, a fact which has been recognized that not even Maxwell himself quite understood how they operated in his general equations of propagation. We need not wonder, then, that Maxwell's followers have not found it a very easy task to understand what his theory really meant and how to work it out. I had occasion to remark, some years since, that it was very much Maxwell's own fault that his views obtained such slow acceptance. And in now repeating the remark, do not abate one jot of my appreciation of his work, which increases daily. For he devoted the greater part of his treatise to the working out and presentation of results, which could be equally well done in terms of other theories, and gave only a very cursory and incomplete exposition of what were peculiarly his own views and their consequences, which are of the utmost importance. Finding these equations of propagation containing the two potentials unmanageable and also not sufficiently comprehensive, I was obliged to dispense with them, and going back to first principles, introduced what I term the second circuital law as a fundamental equation, the natural companion to the first. The change is, I believe, a practical one, and enables us to considerably simplify and clarify the treatment of general questions, whilst bringing to light interesting relations which were formerly hidden from view by the intervention of the vector potential A and its parasites J and psi. Another rather curious point relates to the old German electrodynamic investigations and their extensions to endeavor to include, supersede, or generalize Maxwell by anti-Maxwellian methods. It would be slaying the slain to attack them. But one point about them deserves notice. The main causes of the variety of formulae and the great complexity of the investigations were, first, the indefiniteness produced by the want of circuitality in the current, and next the potential methods employed. J. Thomson's report on electrical theories contains an account of many, as a very full example, that most astoundingly complex investigation of Clausius in the second volume of his Mechanische Wärmetheorie may be referred to. But if the critical reader will look through these investigations and eliminate the potentials, he will find as a useful residuum the second circuital law, and, bringing it into full view, will see that many of these investigations are purely artificial elaborations, devoid of physical significance, gropings after Mars' nest, so to speak. Now, using this law in the investigations, it will be seen to involve, merely as a matter of the mathematical fitness of things, the use of another, the first circuital law, and so to justify Maxwell in his doctrine of the circuitality of the current. The useful moral to be deduced is, I think, that in the choice of variables to express physical phenomena, one should keep as close as possible to those with which we are experimentally acquainted and which are of dynamical significance, and be on one's guard against being led away from the straight and narrow path in the pursuit of the will-o', the wisp. As regards the terms in the expression of the second law, which stand for unknown properties, they may be regarded merely as mathematical extensions which, by symmetrizing the planar, and sometimes assist working out. But some other extensions of meaning, yet to be considered, have a more substantial foundation. Meaning of true current criterion. 66. One of these extensions refers to the meaning to be attached to the term current, electric or magnetic respectively. As we have seen, electric current, which was originally conduction current only, had a second part, the displacement current, added to it by Maxwell to produce a circuital flux. And further, when there is electrification in motion, we must, working to the same end, add a third term, the convection current, to preserve circuitality. A fourth term may now be added to make up the true current when the medium supporting the fluxes is in motion. Thus, let us separate the motional electric and magnetic forces from all other intrinsic forces that go with them in the two circuital laws, voltaic, thermoelectric, etc. 39, denoting the former by E and H, and the latter by E0 and H0. The two equations of circuitation 12, 13 from paragraph 38, and 6, 7 from paragraphs 52 now read, here equations 1 and 2. Now transfer the E and H terms to the right side, producing two equations here, equations 3 and 4, where J and G are auxiliaries before used, given by J equals curl small h, G equals minus curl small e. It is the new vectors J0 and G0, which should be regarded as the true currents when the media moves, as the auxiliaries J and G are themselves circuital vectors, There may not at first sight appear to be any reason for further complicating the meaning of true current when separated into component parts, for the current J is circuital, and so is J0, which is of course the same as J when the medium is stationary. The extension would appear to be an unnecessary one, of a merely formal character. On the other hand, it is to be observed that from the Maxwellian method of regarding the current as a function of the magnetic force, the extended meaning of true current is not a further complication but is a simplification. For whereas in the equation 2 we deduct from the force E of the flux not only the intrinsic force small e0, but also the motional force small e to obtain the effective force whose curl measures the current. On the other hand, in 4 we deduct only the intrinsic force. Away, therefore, from the sources of energy which are independent of the motion of the medium, the force whose curl is taken in 4 is the force of the flux, which specifies the electric state of the medium, whether it be stationary or moving. Trick current, although there is no magnetic force, but according to the other way there is no true current, and the absence of magnetic force implies the absence of true electric current. But still this question remains, so far, somewhat of a conventional one. Is there any test to be applied which shall effectually discriminate between J and J0 as the true current? There would appear to be one and only one, viz., that E0 being an intrinsic force, its activity, whatever it be, say E0x, expresses the rate of communication of energy to the electromagnetic system from a source not included therein, and not connected with the motional force E. When the medium is stationary, x is J, and the question is x to be J or J0 or anything else when the medium moves? Now this question can only be answered by making it a part of a much larger and more important one. That is to say, by a comprehensive examination of all the fluxes of energy concerned in the equations 1, 2, or 3 and their mutual harmonization. This being done, the result is that E0J0 is the activity of E0, so that it is J0 that is the measure of the true current with the simpler relation to the force of the flux. And it is naturally suggested that in case of further possible extensions, we should follow in the same track and consider the true current to be always the curl of large H minus H0, independently of the make-up of its component parts. This is not the place for a full investigation of this complex question, but the main steps can be given, not for the exhibition of the mathematical working, which may either be taken for granted or filled in by those who can do it, but especially with a view to the understanding in a broad manner of the course of the argument. Up to the present I have used the notation of vectors for the concise and plain presentation of principles and results, but not for working purposes. This course will be continued now. How to work vectors may form the subject of a future chapter. It is not so hard when you know how to do it.